Welcome! Today, we'll explore problem number 1648, sell diminishing valued colored balls. In this problem, we'll navigate through an optimization challenge involving diminishing returns from selling colored balls. Let's dive into the details and solve it step by step. The problem involves selling colored balls from an inventory, where each ball has a diminishing value after it's sold. The inventory array specifies the number of balls available for each color, and orders tells us how many balls the customer wants to buy in total. Each ball is sold for its current value, and the value decreases by 1 after each sale for balls of the same color. If a ball's value reaches 0, it can no longer be sold. The goal is to maximize the total value achieved from selling exactly orders balls. Since the result could be very large, we need to return the total value modulo 10 to the power of 9 plus 7. The input format consists of the inventory array and the order's integer, and the output is a single integer representing the maximum total value modulo 10 to the power of 9 plus 7. Let's look at an example to better understand the problem. Suppose the inventory is 2, 5, and the customer wants to buy 4 balls. The output is 14. Here's how we achieve that. First, we sell 1 ball of value 5, reducing the inventory to 2, 4, and adding 5 to the total value. Next, we sell 1 ball of value 4, reducing the inventory to 2, 3, and adding another 4 to the total value, which now becomes 9. Then, we sell 1 ball of value 3, reducing the inventory to 2, 2, and adding 3 more, making the total 12. Finally, we sell 1 ball of value 2, reducing the inventory to 2, 1, and adding 2, reaching the maximum value of 14. This step-by-step process shows how we maximize the total value by always selling the highest value balls first. Another example highlights the process further. If the inventory is 3, 5, and the customer wants 6 balls, the output is 19. Here's the breakdown. Start by selling 1 ball of value 5, leaving 3, 4 in the inventory, and adding 5 to the total. Next, we sell a ball of value 4, leaving 3, 3, and adding 4 to make the total 9. Then, we sell a ball of value 3, reducing the inventory to 2, 3, adding 3 to the total for 12. Another ball of value 3 is sold, leaving 2, 2, and making the total 15. We then sell 2 balls of value 2 consecutively, reducing the inventory to 2, 0, and adding 4 more to reach the final total of 19. This example shows how the inventory shifts after each sale while prioritizing higher value balls to maximize the total. In a larger scale scenario, consider an inventory with a single color containing 100,000 balls and a customer who wants all 100,000 of them. The output is 500,005,000. This is calculated as the sum of the first 100,000 integers, starting from 100,000 down to 1. The formula for this sum is n asterisk, n plus 1, slash 2, where n is the number of balls, giving us 100,000 asterisk 100,001 slash 2, which equals 500,005,000. Since this value is already less than 10 to the power of 9 plus 7, no modulo operation is needed. This example demonstrates how to handle cases where all balls are sold from a single color and the total value can be computed mathematically without iterating through each sale. Finally, it's important to note that the constraints of the problem require an efficient solution. The inventory length can be as large as 10 to the power of 5, and each color can have up to 10 to the power of 9 balls. A naive approach that simulates each ball sale one by one would be far too slow for these input sizes. Instead, an optimized method is needed, such as using binary search or a heap-based approach. These techniques allow us to quickly determine the order of ball sales and efficiently calculate the maximum total value without iterating through every possible sale, ensuring the solution meets the time complexity requirements. To solve the problem, one approach we could consider is the brute force method. The intuition here is straightforward: sell 1 ball at a time, always selecting the ball with the highest value. After selling a ball, we decrease its value by 1 and repeat the process until we fulfill all the orders. To implement this, we can use a max heap, which allows us to efficiently retrieve the ball with the highest value. Each time we sell a ball, we decrease its value and reinsert it into the heap if it still has a positive value. While this approach is simple to understand and implement, it has significant drawbacks in terms of efficiency. Building the initial heap requires O(n) time, and for each of the orders, retrieving and reinserting into the heap takes O log n. This means that the total time complexity becomes O orders asterisk log n. For very large values of orders, such as 10 to the power of 5 or 10 to the power of 6, this approach becomes computationally expensive and impractical. Therefore, we need a more efficient solution. A more optimized approach involves using binary search to group sales by ranges of ball values rather than processing each sale individually. The key idea is that, instead of selling balls one by one, we can sell all balls of a certain value together, reducing their value as a group. For instance, if the highest valued balls are worth 8 and there are 3 of them, we can sell all 3 at once and reduce their value to 7, drastically reducing the number of operations. There are 2 important observations that make this approach work. First, the values of the balls follow a predictable decreasing pattern, and we can calculate the revenue from a range of values using the formula for the sum of an arithmetic series. Second, by using binary search, we can efficiently determine the lowest value the balls will reach after fulfilling all orders. The steps are as follows. First, sort the inventory in descending order. Then, use binary search to find the minimum value of the balls after selling all the orders. At each midpoint of the search, calculate how many balls can be sold and compare it to the number of orders. Once the target value is determined, the total revenue can be calculated by summing up the contributions from each range of values using the arithmetic sum formula. This method is much more efficient, with a total time complexity of O(n) log n plus log max underscore value asterisk n, where max underscore value represents the highest initial value in the inventory. The binary search approach is preferred because it is significantly more efficient than the brute force method. By focusing on ranges of ball values instead of individual sales, it reduces the number of operations required, making it a better choice for this problem. The use of the arithmetic sum formula allows us to compute the revenue from a range of values in constant time, which further speeds up the process. This makes the approach particularly effective for large values of orders, such as 10 to the power of 9, where the brute force method would be infeasible due to repetitive operations. However, there are trade-offs to consider. While the binary search approach is more complex to implement, involving arithmetic sums and careful range calculations, this added complexity is justified by the dramatic improvement in time efficiency. On the other hand, the brute force method is simpler to code and may be adequate for smaller inputs, but it quickly becomes impractical as the size of the input grows. The binary search approach strikes an excellent balance between efficiency and clarity, making it the optimal solution for the cell diminishing valued colored balls problem. It handles both small and large inputs effectively, minimizing redundant calculations and leveraging arithmetic properties to simplify the process. By focusing on ranges of values instead of individual operations, this approach provides a clean and scalable solution. This strategy not only ensures high performance for large test cases but also offers a structured way to maximize revenue efficiently. To tackle this problem effectively, we start by understanding the core objective. We need to sell a specific number of balls, represented by the orders variable, from an inventory where each ball has a value. The twist is that after selling a ball, its value decreases by 1. Our goal is to maximize the revenue generated from this process. For example, if our inventory has balls with values 3, 5, 7, and we need to sell 4 balls, the optimal strategy would be to sell the highest valued balls first, 7, then 6, then 5, and finally 3, maximizing the total revenue. This brings us to some important observations. The most critical insight is that to maximize revenue, we should always sell the ball with the highest current value. Once a ball is sold, its value decreases, and the next highest value might belong to a different ball. To manage this efficiently, we use a max heap data structure. A max heap is perfect for this scenario because it allows us to retrieve and update the highest value quickly. Since Python's heap module implements a min heap by default, we can simulate a max heap by storing negative values. This way, the largest value remains at the root of the heap, ready to be accessed efficiently. Now that we have a max heap ready, we can begin the main algorithm. First, we initialize a variable, revenue, to 0. This will keep track of the total revenue as we sell balls. The process involves a loop that continues until all orders are fulfilled. At each step, we extract the largest value from the heap. Since we stored negative values for max heap behavior, we convert the extracted value back to positive. With this value, we calculate how many balls can be sold. If there are other balls with the same value, we sell as many as possible without exceeding the orders. If the next highest value is lower, we sell balls within the range of values between the current maximum and the next highest value. This step ensures that we maximize revenue while efficiently managing the inventory. Once we determine the number of balls sold, we update the orders by deducting this amount and add the revenue generated to our revenue variable. If the balls value decreases but remains above 0, we push this reduced value back into the heap for further processing. Once all orders are fulfilled, we return the total revenue. This approach is robust and handles scenarios like duplicate values seamlessly, as the max heap automatically prioritizes the highest available value. In cases where the number of orders exceeds the total number of balls in the inventory, the algorithm needs to handle this gracefully. It does so by limiting the number of sellable balls to what's available, ensuring no errors occur. A deeper look into the problem reveals that the greedy approach is the most effective strategy here. By always selling the highest value ball available, we ensure that the revenue is maximized at every step. The use of a max heap is key to this efficiency. It allows us to retrieve and update the largest value in logarithmic time, which is far more efficient than repeatedly sorting the inventory. Additionally, we can optimize further with a mathematical approach. Instead of selling balls one at a time, we can sell them in bulk across ranges of values. For instance, if the two highest values are 7 and 5, we can sell all balls with values 7 and 6 in one operation. This bulk selling approach significantly reduces the number of heap operations, making the algorithm faster while maintaining accuracy. The combination of a greedy strategy, heap efficiency, and mathematical optimization makes this solution both elegant and scalable. Let's summarize the key variables and analyze the algorithm's complexity. The variable revenue tracks the total revenue generated, while orders keeps count of the remaining balls to be sold. The time complexity of the algorithm is driven by heap operations. Both inserting into and extracting from the heap take log n time. In the worst-case scenario, where we sell balls one by one, we perform a heap operation for every ball sold, resulting in a time complexity of orders log n. However, when we apply the mathematical optimization to sell balls in bulk, the number of heap operations decreases, leading to an improved runtime. As for space complexity, the heap itself requires n space, where n is the size of the inventory. Additional variables, like revenue and orders, use only one space. This makes the algorithm space efficient as well as time efficient. Overall, the combination of a max heap, mathematical optimization, and greedy principles ensures that the solution is both optimal and performant for large inputs. Here, we begin by defining a class called solution and implementing the max profit method, which takes two arguments, inventory and orders. The variable mod is initialized to 10 to the power of 9 plus 7 to ensure that our final result fits within the required modulo constraints. We then sort the inventory list in descending order to simplify the process of accessing the highest valued colored balls first. Additionally, we append a 0 to the inventory to handle edge cases and simplify the calculations when we reach the end of the list. Next, we initialize result to store the cumulative profit and n to represent the number of balls with the same value, starting with 1. The loop iterates through the inventory, and for each ball value, we calculate the difference in height or value between consecutive groups of balls using height_diff. If the number of orders can cover all the balls in this height range, we calculate the profit for the entire range using the sum of arithmetic sequences formula. Specifically, we subtract the sum of the next lower range from the current range, multiply this by n, and add it to the result. The number of orders is then reduced accordingly. If the orders cannot cover all the balls in the current height range, we calculate how many complete rows of balls we can take, represented by full_rows, and how many balls will remain as a remainder. Using these values, we calculate the profit for the fully covered rows using the same arithmetic sequence formula, adjusting for the reduced range. The remaining profit from the leftover balls is added based on their value, and we break out of the loop since all orders have been fulfilled. At the end of each iteration, we increase n to include the next group of balls, which have the same value as the current group. Finally, we return the result modulo mod to ensure compliance with the problem's constraints and complete the implementation. Here, we begin our Java implementation by importing the necessary utilities and defining the solution class. The main method, maxProfit, calculates the maximum profit from selling diminishing-valued colored balls given the inventory and the number of orders. First, we declare a constant mod to handle modular arithmetic, ensuring our results stay within bounds for large numbers. Next, we sort the inventory array in descending order to prioritize selling the most valuable balls first. The variable n stores the length of the inventory array, result accumulates the total profit, and count keeps track of how many balls exist at the current level of value. The for loop iterates over the inventory array starting from the most valuable ball, identified by current. The variable next holds the value of the ball at the next level of the array or 0 if there's no next level. The key calculation here is heightDiff, which represents the difference in value between the current and next levels. If the remaining orders are sufficient to sell all balls between the current and next levels, we calculate the profit using the helper method SumRange to sum the values in this range, multiply it by count, and add the result to the total profit. We also deduct the corresponding number of orders. However, if we don't have enough orders to clear this range completely, we'll sell only a portion, as we'll see next. If we can only partially sell the balls at the current value level, we calculate the number of complete rows, or full levels, to sell using integer division of orders by count. The remainder represents any leftover orders that can only sell a fraction of the balls. To handle this, we first calculate the profit from the full rows using SumRange and add it to the result. Then, the profit from the remaining balls is computed by multiplying the remainder with the value of the next level after the full rows. At this point, all orders are fulfilled, so we set orders to 0 and break out of the loop. Finally, we return the result modulo mod to ensure the output stays within the bounds of the problem constraints. The helper method SumRange is defined to calculate the sum of integers from start to end inclusively, using the formula for the sum of an arithmetic series. This method is key to efficiently calculating profits over a range of values without iterating through each number. Together, these parts form a solution that efficiently handles the constraints of the problem. In this example, we start with an inventory of 3, 5, and need to fulfill 6 orders. First, we sort the inventory in descending order, resulting in 5, 3, and append a 0 to simplify calculations, so the array becomes 5, 3, 0. We also initialize some variables. Mod is set to 10(9 plus 7 for modular arithmetic, result is initialized to 0 to store the total profit, and n starts at 1, representing the number of balls at the current value. Now, in the first iteration, we're looking at the difference between the first two inventory levels, 5 and 3, which gives us a height_diff of 2. Since we have enough orders to cover this difference, we calculate the profit from selling balls at these levels. Adding the profit from this range, we get result plus equals 9. We then reduce the remaining orders by 2, leaving 4, and update n to 2, accounting for the next group of balls in the inventory. In the second iteration, we're looking at the next difference between inventory levels, 3 and 0, which gives a height_diff of 3. However, we don't have enough orders to cover this entire range, as 4 is less than 2*3. So, we calculate how many full levels of balls we can take. Dividing the remaining orders by n gives full_rows equals 2, and since there's no remainder, we take exactly 2 full rows. Adding the profit from these rows, we get result plus equals 13. With no orders remaining, we exit the loop. Finally, we return the result modulo 10(9 plus 7, which gives us a total profit of 22 for this example. In the second example, the inventory is 2, 8, 4, and we need to fulfill 8 orders. After sorting in descending order and appending 0, the inventory becomes 8, 4, 2, 0. We initialize result to 0 and n to 1. For the first iteration, the difference between 8 and 4 is 4. Since we have enough orders to cover this range, we calculate the profit from selling balls at levels 8, 7, 6, and 5, which totals 26. After deducting the 4 orders used here, we're left with 4 orders, and we update n to 2. In the second iteration, the difference between 4 and 2 is 2. Again, we have enough orders to cover this range, so we calculate the profit from selling balls at levels 4 and 3, multiplied by n, which adds 14 to the result. With all orders exhausted, we proceed to the final step. At this point, the loop terminates since we've fulfilled all orders. The total profit accumulated in result is 40. We return this value modulo 10(9 plus 7, which gives the final output of 40 for this example. Now, let's consider a third example where the number of orders exactly matches the available inventory levels. In this third example, the inventory is 10, 8, 6, and we have 10 orders to fulfill. After sorting and appending 0, the inventory becomes 10, 8, 6, 0. We initialize result as 0 and n is 1. In the first iteration, the difference between 10 and 8 is 2. Since we have enough orders, we calculate the profit from this range, which adds 19 to the result. We then reduce the orders by 2, leaving 8, and update n to 2. In the second iteration, the difference between 8 and 6 is also 2. Again, we can cover this range, so we calculate the profit for 2 levels, multiplied by n, resulting in an additional 30 added to the result. This leaves us with 4 orders, and n is updated to 3. In the third iteration, the difference between 6 and 0 is 6, but we don't have enough orders to cover this entire range. Since the remaining orders are fewer than the required amount to fully cover the range, we calculate the profit from partial rows. Dividing the orders by n gives full_rows equals 1, and the remainder is 1. The profit from these rows is calculated as result plus equals 40, which includes the contribution from the full rows and the remainder. With no orders left, the loop ends. Finally, we return the result modulo 10(9 plus 7, which gives a total profit of 40 for this example. This concludes the step-by-step walkthrough for this problem. The time complexity of the solution is determined by several factors. First, we need to sort the inventory list in descending order using the sort function. Sorting an array of size n takes n log n in the worst case. Once the inventory is sorted, we iterate through the list using a for loop. This loop processes all n elements in the inventory, and each iteration involves operations like arithmetic calculations, comparisons, and updates. Importantly, the calculation of the sum of an arithmetic series, such as inventory I * inventory I plus 1 / 2, is a constant time operation. So, the operations within the loop are O(1) for each iteration, resulting in a total contribution of O(n) from the loop. Finally, while the orders are reduced within the loop, this does not increase the complexity further because the number of iterations is still limited by the size of the inventory. Therefore, the two main contributors to the time complexity are the sorting step and the traversal of the inventory. When we combine the contributions to the time complexity, the dominant factor is the sorting step, which takes n log n. The loop adds n, but this is overshadowed by the sorting. As a result, the overall time complexity of the solution is n log n. Now, looking at the space complexity, the inventory list itself occupies n space, as it contains n elements. Beyond this, the algorithm uses a constant amount of auxiliary space for variables like mod, result, n, and orders. Even the 0 appended to the inventory adds only a single integer, which is insignificant in terms of space usage. Therefore, the space complexity is determined primarily by the input storage, which is n. Summarizing the space complexity, no additional data structures are used apart from the input inventory array and a few scalar variables. This leads to an overall space complexity of n. Now, let's analyze the best, average, and worst cases for the solution. In the best case, the inventory array is already sorted in descending order, meaning the sorting step could potentially be negligible if a stable sorting algorithm is used, leaving only the loop to run for all n elements. This results in n for the loop, but since sorting still dominates, the overall time complexity remains n log n. In the average case, with random input, the sorting step continues to dominate, and the loop contributes n, keeping the overall complexity as n log n. In the worst case, the behavior is similar to the average case, where sorting is required and all elements are processed in the loop, again leading to n log n as the overall complexity. Let's compare the optimized approach with a naive or brute force method. A naive approach would involve repeatedly selecting the highest value in the inventory, decrementing it, and adding the value to the result until all orders are fulfilled. This would require finding the highest value repeatedly, which takes O(n) for each search. Performing this for all orders would result in a time complexity of O(n** orders. This becomes extremely inefficient, especially when orders is large. The optimized approach, on the other hand, sorts the inventory once in O(n log n), and uses a greedy strategy to efficiently calculate the sum of values for groups of balls with the same value. Instead of decrementing values one by one, it handles ranges of values at once, significantly reducing the number of operations needed to fulfill the orders. This optimization reduces the time complexity from O(n** orders to O(n log n). Finally, let's confirm the proof of complexity. The sorting step clearly takes O(n log n), as it uses a comparison-based sorting algorithm. The loop iterates at most n times, performing constant time operations such as arithmetic calculations and comparisons during each iteration. This contributes an additional O(n). Furthermore, calculating the sum of an arithmetic series, like inventory I** inventory I plus 1 / 2, is a constant time operation, adding O(1) per iteration. When we combine these, the overall time complexity is dominated by the sorting step, leading to O(n log n). For space complexity, the input inventory array occupies O(n) space, and the algorithm uses only a small amount of constant auxiliary space. Therefore, the space complexity is O(n). This confirms the efficiency of the solution both in terms of time and space usage. When working through this problem, there are a few common mistakes to watch out for. First, a frequent issue is incorrectly decrementing the ball values. Either forgetting to reduce the ball's value after selling it, or decrementing it too many times, can cause the total earnings calculation to go wrong. This is especially problematic in cases where the ball values significantly impact the result, leading to failed test cases. Another mistake is inefficiently sorting the inventory during every iteration of a brute force approach. Sorting repeatedly is computationally expensive and can lead to time complexities like O(n² log n, or worse, which won't scale for larger inputs. Finally, overlooking edge cases can cause problems. For instance, if the number of orders exceeds the total number of balls available, you might run into index out-of-bounds errors or incorrect outputs when orders can't be fulfilled properly. These issues can derail your solution, so it's important to handle them carefully. Another mistake to avoid involves floating-point arithmetic. Using floating-point calculations for large numbers can introduce precision errors. These errors can have a significant impact, especially when modulo operations are required, as they depend on precise integer results. Speaking of modulo operations, it's also easy to overlook applying the modulo constraint to your final output. Many problems, including this one, specify that results should be returned modulo 10 to the power of 9 plus 7. Failing to do so can result in incorrect answers for large test cases where integer overflow comes into play. These details may seem minor, but they're critical for ensuring your solution is robust and meets all problem constraints. Now, let's focus on how to approach this problem effectively in an interview setting. Optimization is key, so always look for ways to reduce redundant operations. For instance, instead of sorting the inventory repeatedly, consider using a max heap or binary search to efficiently retrieve the highest ball value. This problem is a classic example of a greedy algorithm or priority queue pattern, so recognizing this structure can help you approach it strategically. Interviewers might introduce constraints that make brute force infeasible, so you should be prepared to explain how optimized approaches like binary search or heaps improve performance. Clear communication is crucial. Make sure you articulate why brute force is inefficient and how your solution justifies trade-offs in complexity. If modulo arithmetic is part of the problem, proactively explain how you'll ensure accuracy and avoid integer overflow. Lastly, reviewing related problems like LeetCode 215 or 502 can help reinforce these concepts and prepare you for similar challenges. There are also several alternative approaches that can help you solve this problem more efficiently. One option is the max heap approach, which allows you to fetch the highest ball value efficiently. After selling a ball, you decrement its value and push it back into the heap if it's still positive. This reduces redundant sorting and brings the complexity down to O and log n, though maintaining the heap does introduce some overhead. Another approach is binary search on earnings. This technique involves pre-sorting the inventory and calculating cumulative sums to determine how many balls can be sold at specific price points. While this adds some implementation complexity, it improves overall efficiency. Finally, you can use a mathematical summation approach, leveraging arithmetic sequences to calculate earnings without iterating over each ball individually. This method is highly efficient, often achieving O and log n, but it requires careful attention to detail to avoid off-by-one errors or boundary issues. Each of these approaches has its trade-offs, so choose the one that best fits the problem constraints and your own strengths. Great job! We've tackled problem number 1648 and learned how to optimize revenue using a greedy strategy. Remember to apply these takeaways to similar problems in interviews and practice sessions. Thanks for joining, see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!